This video is for topic 8.3, weak acid and base equilibria. The objective for this topic is to explain the relationship among pH, pOH, and concentrations of all species in a solution of monoprotic weak acids or weak bases. So unlike strong acids and bases, weak acids and bases react with water to produce hydronium ion and hydroxide ion, and when they do that, they only partially ionize. This means that the assumptions that we made with strong acids and bases, where the concentration of the acid and base is equal to the concentration of the hydronium or the hydroxide ions, does not apply here. Because they only partially ionize, there's some amount of the acid or base remaining, as well as the separate parts of the ions. The percent ionization can be calculated from the pKa or the pKb, which would be the negative log of the equilibrium constants for either the acid or the base, and the initial concentrations of the acid or base. We're going to look at several examples where we're going to apply what we already know about chemical equilibrium and apply them to acid and base equilibria. So in this question, it asks about an aqueous solution of lactic acid, which is a weak acid, which has a pH of 2.43, and we want to know what the value of the Ka is for the lactic acid. So since we're looking for an equilibrium value, we're going to go ahead and write our equation and start with an ice table. So we have our CH3CHO CO2H, which is our very long formula for lactic acid. And in solution, because it's a weak acid, it deprotonates, but only some of it deprotonates, some of it stays as the lactic acid protonated form. So we're going to write some of it without, means it needs to not have the hydrogen. There we go. And then we have our hydrogen ion. Okay, so if we think about this in terms of an ice table, our original concentration of our lactic acid to start with is 0.10 molar, which means before any deprotonation has happened, we have 0 for our concentration for our two ions. So then our lactic acid is going to go down by X. Our products go up by X. So at equilibrium, we have 0.1 minus X, X, and X. Now, our pH tells us the concentration of our hydrogen ion. So pH is the negative log of the hydrogen ion concentration. We're told that our pH is 2.43. So then we can solve for our hydrogen ion concentration. So we do the inverse log of negative 2.43, which gets us a hydrogen ion concentration of 3.7 times 10 to the negative 3. So that tells us what our value of X is. So we know at equilibrium, our hydrogen ion is 3.7 times 10 to the negative 3. We know that our lactate ion, I think it is, would also be 3.7 times 10 to the negative 3. And then our lactic acid would be 0.1 minus that amount, which gets us 0.0963. So it's asking us for the Ka value, so we're going to go ahead and write our equilibrium expression. So we have our products divided by our reactants. And then we just have to plug the values in. So we have 3.7 times 10 to the negative 3, 3.7 times 10 to the negative 3, divided by 0.0963. We end up with a Ka value of 1.4 times 10 to the negative 4th. So this question asks us to calculate the pH of a solution of benzoic acid, given the Ka value for the acid, and we're given the equilibrium reaction equation. So we know that if we want to, so this is a weak acid, okay? So since it's a weak acid, we know that the concentration of the acid is not going to equal the concentration of the hydrogen ion. So the concentration of C6H5CO2H does not equal the concentration of the hydrogen ion, so we can't just use that directly to calculate pH. We still, though, do need the concentration of the hydrogen ion, because that's how we calculate pH. Okay, so that's where we're starting with. So we need to figure out how we're going to get to the hydrogen ion concentration. Now, in this particular reaction, our hydrogen ion is represented by the hydronium ion, which is water with an extra hydrogen, which is another way to talk about a proton or a hydrogen ion. So this is the part of the reaction we're going to be looking at. If we need to know that concentration and it's in equilibrium, we're going to be using an ice table. Okay, so I'm going to erase all my starting doodles, because now I have a bit of a direction. So I'm going to start with my ice table. My initial concentration of my benzoic acid is 0.20. I'm given that in the problem. I can ignore the water because it's not going to show up in the equilibrium. And I don't have any of my product ions to start with. So then my benzoic acid is going to go down by X. My hydronium will go up by X. And my benzoate ion is going to go up by X as well. So that means at equilibrium, we have 0.2 minus X, X, and X. So let's look at my equilibrium expression. So Ka is going to equal, we'll do products divided by reactants and then we're going to plug in the values that we have for each of these. So we have X times X divided by 0.20 minus X, which is X squared over 0.2 minus X. And then we're given the Ka value. So we're told that the Ka is 6.3 times 10 to the negative fifth. Now, because we have the minus X in the denominator, we could work this out using a quadratic. So we'd move the denominator over to the right-hand side by multiplying it by the Ka. Then we'd move it back over to the left. We'd have a quadratic equation. We could solve for our X value. The other thing we could do is we could look at the value, the magnitude of Ka. Ka is really, really small. We know that because it's times 10 to the negative fifth. So because it's a really, really small value, there isn't going to be a significant decrease in the concentration of the benzoic acid. A really small Ka means that the equilibrium is going to favor the reactants over the products. So it's going to favor the benzoic acid over either of the ions. So we can simplify this to say X squared over 0.2 equals 6.3 times 10 to the negative fifth. So we're saying that that is a negligible change in the concentration. If you don't feel comfortable doing that, you can always work it out using the quadratic. But using our assumption, that gets us an X value of 1.1 times 10 to the negative 3. And that is our hydrogen ion concentration. So, well, in this case, hydronium. So my hydronium ion concentration is 1.1 times 10 to the negative 3, which means my pH is going to be negative log of 1.1 times 10 to the negative 3, which gets me a pH value of 2.96. as my answer. This question is asking us about the pH of a solution of sodium acetate, and we're given the Kb value for the acetate ion. Now, the issue with this is that sodium acetate is neither obviously an acid or a base. So, since we're given the Kb value for the acetate ion, we're going to start with that. So we're going to start by looking at how our sodium acetate is going to break up. Granted, this reaction isn't really going to have an overall effect on our final answer, but I find it helpful to visualize what's going on. So our sodium acetate is going to break up in solution into sodium ion and acetate ion. And we're going to make the assumption that it completely dissociates, it completely breaks up. Sodium acetate is going to be assumed to be a very soluble compound. So that tells us that if we have a 0.015 molar solution of sodium acetate, that means we have a 0.15 molar solution of sodium and 0.015 molar solution of acetate ion. So that assumption is going to get us here. Now, this is happening in water, and we haven't accounted for the water yet. So this is where we're going to see what happens to the acetate ion in water. So our CH3CO2 minus is going to react with liquid water, and this is going to be in equilibrium. So the acetate ion is the conjugate base of the weak acid acetic acid, which is vinegar. So it's going to take a hydrogen from the water to form acetic acid. And then that's going to leave our water with a hydroxide ion. Now this is in equilibrium because this is a weak acid and it's weak, or a weak base, because a base is going to accept a hydrogen. So this is a weak base reaction going on here. So now we're going to look at an equilibrium for this. So we're going to set up our ice table. We made the assumption from our first step that everything dissociated, which means that we know our initial concentration of our acetate ion. So 0.015. We have no acetic acid and we have no hydroxide to begin with. And then we're going to go down by X and up by X, which means at equilibrium we'll be at 0.015 minus X, X, and X. Okay, so as it's written, this is a weak base reaction because the acetate ion is accepting a hydrogen to form the conjugate acid and hydroxide, which is appropriate because we're given the Kb value. So we'll go ahead and set up this expression. So Kb is going to be the products divided by the reactants, which then when we substitute in our values at equilibrium gets us X and X, and then 0.015 minus X. And we're told that our Kb value is 5.6 times 10 to the negative 10th. Now, we could work this out and solve the quadratic, or we could look at our Kb value and notice that it's a very, very small number, which means that it's going to very much favor the reactants over the products. So most of it is going to stay as the acetate ion, which means we're going to have very little change in the concentration of the acetate ion. So we can make the assumption that 0.015 is essentially not going to change. So that simplifies to x squared divided by 0.015 equals 5.6 times 10 to the negative 10th. That gets me then an x value of 2.9 times 10 to the negative 6, which is both my acetic acid concentration as well as my hydroxide concentration. And the hydroxide ion concentration is going to be the useful one here. With that number, with that concentration, we can calculate the pOH. So I'm going to scroll down a little bit to give us some more space. So pOH is the negative log of the hydroxide ion concentration. So we can't use the acid because it's a weak acid, so the concentration of the weak acid does not equal the concentration of the hydrogen ion. So we have to go with the hydroxide. So we're going to go ahead and find the pOH, so that's negative log of 2.9 times 10 to the negative 6, which gets me a pOH value of 5.5. Now we know that, pH plus pOH equals 14. Or we could write this as pH equals 14 minus pOH. Because the question doesn't ask about pOH, it asks about pH. So we've got one more step. So then pH equals 14 minus 5.5, which gets us a pH value of 8.5.